Have you ever just stopped and thought about how energy in a complex system actually behaves? It doesn't just wander around aimlessly, right? It needs direction, structure, and a set of unbreakable rules to get from point A to point B. Whether we're talking about electrical circuits, mechanical engines, or hydraulic pumps, energy distribution is highly regulated. Okay, let's dive into this explainer and discover exactly how engineers map out that power flow using a brilliant visual tool known as bond graphs. It's a totally fascinating question, isn't it? How exactly does energy know where to flow? Well, the answer lies in understanding that engineering systems have invisible regulators. Think about a busy intersection in the heart of a major city during rush hour. If you didn't have traffic controllers or traffic lights, you just have absolute chaos, cars crashing, gridlock, the whole shebang. Energy in a dynamic system acts the exact same way. It relies on these hidden logical traffic controllers to dictate exactly how, when, and where power gets distributed. Section 1. Meet the traffic controllers. Let's actually meet the tools engineers use to logically map these systems out, starting with the fundamental math. Section 2. Zero junctions, shared effort. Let's break down the very first type of traffic controller we'll be analyzing today. Here's our formal definition of the zero junction. It represents a connection of common effort. So the crucial point is that whenever elements in a system share the exact same effort, they're connected by a zero junction. If you've got an electrical background, you can think of this directly in terms of parallel systems and Kirchhoff's current law. The effort, or, the voltage in electrical terms, is shared equally across the parallel branches, while the flow actually splits. The zero junction perfectly captures that fundamental behavior. Section 3. One junctions, common flow. Now let's flip the coin and see how the second type of traffic controller operates. Enter the one junction. This connection is all about common flow. When elements are connected by a one junction, the flow running through them is identical. Going right back to our electrical equivalent, this directly corresponds to series systems and Kirchhoff's voltage law. In a series circuit, the current, the flow, is exactly the same through every single component, while the effort is what actually divides. Seeing them side by side really clarifies the concept, doesn't it? And this brilliantly illustrates the beautiful symmetry in bond graph logic. The zero junction handles common effort in parallel systems governed by Kirchhoff's current law, while the one junction handles common flow, and series systems governed by Kirchhoff's voltage law. They're basically a perfectly matched pair of traffic controllers, dictating the dual nature of energy distribution literally no matter what kind of physical system you're analyzing. Section 4. Visual memory tools. Let's look at some super effective visual mnemonics to make memorizing these abstract laws incredibly intuitive. Just picture a parallel circuit in your mind for a second. You've got a single wire that splits into two separate parts, routes around, and then rejoins. What shape does that physically create? Well, it makes a circular path. It quite literally looks just like the number 0. So whenever you see a parallel system sharing effort, just picture that circular splitting and rejoining wire, and boom, you'll instantly remember it's a zero junction. Let's move to and see how this builds with the other junction. Think about a series connection. It's a single, uninterrupted, straight, linear path, right? It doesn't split, the flow just powers straight through. And a straight line looks exactly like the number 1. It's almost too simple, but connecting the mathematical laws to these intuitive physical shapes ensures you're never going to mix up your 0 and 1 junctions again. Section 5. The engineering challenge. Let's gamify this explainer and drop these traffic controllers into a real-world scenario to test your mastery. Okay, here's your scenario. Imagine you're the engineer, and you're handed a mechanical mass spring damper system. You've got a mass, a spring attached to it, and a damper, like a shock absorber, regulating its movement. We aren't talking about electrical circuits anymore. We're in the world of physical, moving mechanical parts. How do you map the power flow here? This is the big question you need to answer. Which junction represents common velocity in the system? I really want you to actively think about this. Pause for a second and apply the traffic controller logic we just went over. If the mass, the spring, and the damper are all experiencing the exact same velocity, do you use a zero junction or a one junction to connect them in your bond graph? Let's break down the logic together. Now, what's really interesting about this slide is how smoothly physical movement connects into bond graph theory. First off, in a mechanical system, velocity basically acts as a type of flow. Since the mass, the spring, and the damper are physically moving together, they all share this common velocity. And we know from our rules that one junctions dictate common flow. Therefore, the one junction is absolutely the correct answer. You'd use a one junction to map the shared velocity of this entire mechanical system. By understanding how a simple 1 or 0 regulates energy, you've literally just simplified some incredibly complex engineering logic. You're now equipped to master power flow across multiple physical domains. So I'll leave you with this provocative thought. Now that you can map the flow of mechanical power with a simple mass spring damper, what other hidden junctions are regulating the dynamic systems all around you? Seriously, look at the technology in your life right now. There's a bond graph waiting to be drawn for all of it. Keep looking for those traffic controllers.